let's look at an example. Suppose I'm looking at a multiple choice test. There's 3 questions, and each question has 4 responses, only one of which is correct. And I want to find out what's the probability that we can just guess at the answers and get 2 questions right. To sort of help with the idea that we are completely guessing, not an educated guess, but an actual just guess, let's suppose that the test is written in Martian. I don't know what language Martian is, but we're just assuming that that's it. So it's a complete guess. Let's first answer, what is the random variable? The random variable isn't like A, B, or C, right? The actual responses that we have in the test. A random variable has to be a numeric measure of the outcome of a probability of experiment. Okay, so I have to have some number that I'm doing. So what we're going to do in this case, since we're interested in whether or not we get 2 questions right, we're going to let our random variable be the number of questions correct. Okay, so then let's ask the question, is this a binomial experiment? And this is where we want to check our 4 criterion. Okay, so our first criterion, are there a fixed number of trials? So in this case, there are n equals 3 trials. That's a fixed number, so first criterion is checked. Next, we want to make sure that the trials are independent. Since we're completely guessing on each trial, getting the first question right has no impact on whether or not we're correct on the second question. So the trials are independent. Next, we want to make sure there are just 2 possibilities, right? We can either get the answers correct or incorrect. And finally, the probability of being correct is the same from one trial to the next. In particular, since there are 3 guesses, remember each question has 4 responses and one of which is correct. So 1 correct out of 4, the probability of guessing a correct answer is p equals 1 out of 4, or 0.25 for each trial. So, since we met all 4 of these criteria, this is a binomial experiment, since all 4 of these properties are met. Okay. Now let's look at another question. What's the probability that in this experiment we actually do get 2 questions right? And in order to think about that, what we're going to do is first look at what is the sample space. This is a random variable, so we're going to look at the sample space of the random variable. Okay. So what we're going to do is we're just going to let the letters R stand for we got the question correct, and W mean we got it wrong. And so we'll just list out 3 in a row, the first, second, and third question. So RRR is all 3 are right. RRW means the first 2 are right and the third one is wrong, which is different from RWR, where we get a right, then a wrong, then a right answer. We have a total now of 1, 2, 3, 4, 5, 6, 7, 8 possible ways that our experiment could come out, right? So 8 things in the sample space. Now, if I want to look at getting just 2 right, then RRW, RWR, and WRR are the only events in the sample space where I have exactly 2 right. Now, here's the problem. We don't just have a 3 out of 8 chance. Okay. The problem here is that getting a question right and getting it wrong are not the same. So when I look at this sample space, not all of these 8 possibilities are equally likely. Remember, we're guessing at each question, so getting all 3 right is going to be more difficult than getting all 3 wrong. Okay, so these events in our sample space are not equally likely, so we're not just looking at 3 out of 8. What we want to do, though, is we want to look at, for each one of these, what's the probability that we actually get it. So let's just look at RRW. Okay, so that means that we get the first question right, the second question right, and the third question right, or sorry, wrong. Since the trials are independent, what we can do is say, well, that's the first one right, and the second one right, and the third one wrong. So our AND rule is multiply. So we can say, okay, probability that we have right on the first times the probability we get right on the second times the probability we get wrong on the third. And since the probability that we get a question right is 1 out of 4, and the second one, probability I get one right is 1 out of 4, and the probability that we get one wrong, well, there's 3 wrong answers out of 4 possible answers, so that's 3 out of 4. So I could just multiply these as decimals and get numbers, but what I want to notice is that this 1 out of 4 is repeated twice. So it's like it's squared. And 3 out of 4 happens just once. This probability is going to be the same for the other two, just in a different order, because we have 2 rights and a wrong, and if I'm multiplying, then the order doesn't matter. Since the probability is the same for all 3 of these, we can sort of just summarize our options below. Now remember that the way that we can get 2 questions right is by either getting this first right, right, wrong, or right, wrong, right, or wrong, right, right. Remember, the OR rule is adding. So I could say it's the probability of the first plus the probability of the second plus the probability of the third. So I'm going to add those probabilities. So there were 3 options, okay, and they're all the same. So I have 3 times 1/4 squared times 3/4 to the first power. Okay. So this is kind of a tedious way to compute this, but it kind of gives you an idea of what's going on. All right. So let's look at the probability of getting 0 right, 1 right, and all 3 right. Using the argument that we just created, what I can do is look at how many different ways can I achieve that event, 0 right, and then I can notice that, well, I'm just looking at the probability of right to the power of how many of those I have, and the probability of wrong to the power of how many of those I have. So to get 0 right, the only way to achieve that is if I have all 3 of them wrong. So there's only one way to get this event, all 3 are wrong. And then I have the probability that I get something correct, but there are 0 of those. And the probability of get something wrong, 3/4 to the power of 3, because I have 3 in a row of those. Getting 1 right, it's going to look a lot like this getting 2 correct answers. Right? Because if I look at my sample space, 1 right has 3 possibilities. And in all 3 of those, I'm going to have 1 correct, have 2 incorrect. Okay. 2 right we already did. 3 1/4 squared, 3/4 to the power of 1. Then all 3 right, the only way to get that event is if all 3 of them are right. So there's only one way to have that combination. And since they're all right, the probability of getting right will be repeated 3 times. The probability of getting it wrong will be repeated 0 times. Okay. This is a very painstaking way to compute out a probability distribution. And there's definitely some patterns to it. The patterns are so good, in fact, that we can come up with a formula. Okay. So I'm going to show you a formula, but we're not going to use the formula directly. Here's our formula. The probability that we get our random variable to be some number is the number of combinations that give us that event times the probability of success to the power of the number of successes times the probability of failure, which is its complement, to the power of how many failures I have. We're never actually going to use this formula in this class. We just include it, to make a nice, neat observation and to tidy things up. What you are going to do is use this calculator function, Binomial PDF. Okay. So keep in mind, you're never going to use the formula, use this calculator function. Okay. Now there's actually 2 calculator functions we'll use. We'll describe them both here in a minute. The first one, the Binomial PDF that we just talked about, will give us one of these probabilities at a time. Okay. So for example, for this 2 right example, we have 3 times 1/4 squared times 3/4 to the power of 1, which gives me 0.140625. Okay. In order to find this out on the Binomial PDF, first we need to explain what some of these pieces are. The Binomial PDF, in order to compute something, needs to know what n is. Right? And our experiment here, n was equal, in the number of trials, right, was equal to 3, because we were looking at 3 multiple choice questions. P is the probability of success. Remember here that that was 0.25. And if I want to look at this probability of getting 2 right, I can think about x being equal to 2. So let me show you how we can go about getting this in our calculator. So here's my calculator screen. I'm going to hit second, and above variables is distributions. So I'm going to have distributions to show me probability distributions, and I'm going to scroll down till I get to the Binomial PDF. Okay. There's a couple here that say Binomial. Remember, one of them is PDF. The other one we'll talk about in a minute. It says Binomial CDF. Now, depending on your calculator, you might get a menu that looks like this: trials, P, and X value. The trials is the N, right? 3P, 0.25, and that X value we set is 2. Depending on your calculator, though, instead of getting that menu that just popped up, you might instead just get Binomial PDF popping up on the screen. And then we're just going to type it in with that same syntax that we wrote down here, n, comma, p, comma, x. So I say, okay, the n is 3, comma, the p is 0.25, comma, the x that we're looking for, first of all, is 2, and I get 0.140625. That's the same thing that we got by using our formula that we came up with painstakingly through observation. Okay. So the Binomial PDF and CDF commands are what we're going to use to compute probabilities when we're using binomials.